Okay, so this time we're doing normal spaces. Last time we introduced the separation axioms, right? And we now going to return to the study of normal spaces, and we'll see that many familiar spaces are normal. Okay, so let's just start. Normal space. First, we have if you're regular plus you are second countable, then you are normal. And the proof is that we give a countable basis, and given two disjoint closed sets, we want to separate them, right? So to separate them, well, as you might guess, we can use the regularity for each x and a. We apply the regularity with b. We have that we know by lemma, we have for any neighborhood u of x, there is a neighborhood v of x such that v bar is contained in u, right? This is by the regularity of x. And we could pick this neighborhood u of x such that it is the separation, right, for between x and b. And we can pick a basis bi such that x is in bi and contain in v, right? And we run through all a. This gives a countable covering of a, right? Say un, and the un and b are disjoint. Un bar and b are disjoint. Okay, so we have this, right? What we mean here is that if we have x and then we have b, right? For u1, u2, right? We can separate them. This is by t3. And again, for this specific u1, we can find another v such that v bar is in our u1. So like this is because we have the arbitrary here, right? And for this v, we can find a basis that is contained in this v. And this collection of vi, we just rewrite it as the UNs, and the UN bar and B are obviously disjoint because UN bars contain VN bar, and VN is subset of U, right? And U, and our U is in fact like our U1 as I just showed you, right? Are empty. So UN and B are disjoint. And by symmetry, we can do the same thing with B. We can pick a covering of B, and each V bar, Vn bar, and A are disjoint. Now we have A is in the collection of union of UNs, and B is in the unions of VNs. They're not necessarily disjoint, so we want to guarantee that they're disjoint. We're going to do something. We're going to manipulate them. So what we're going to manipulate is that we fix the index m, we define um prime, the new um, as our original subtract the union of the vi bars, or the union from 1 to m. And similarly for vm prime, our new vm prime is equal to the old vm subtract the ui's, or I runs from 1 to n. They are open, right? Because why? Because this is a closed set. This is a closed set, right? You subtract by the closed set is basically intersecting some complement of a closed set, which is intersecting an open set. And um is also open. So u prime m and v prime m are open, and we want to show that their union are disjoint. So, well, by a set theory, their intersection is the union of ij's of ui prime intersect vj prime. So with that loss of generality, right? If we have I as less than or equal to j, then ui prime will be ui and the union of vk's, right? And this is obviously contained in the ui's. Now for this vj, v prime j is old vj subtract the uk bars, right? But ui prime is contained in ui. And since I is less than or equal to j, it is contained in this union, right? Ui is contained in this union here, right? So v prime j is vj subtract by those things, and ui is contained in this, and ui prime is contained in ui. So obviously we have they are disjoint. for any I and any j. So that's why I said without loss of generality, if I less equal to j, ui prime and vj prime are disjoint. And the union of ui prime covers a, right? Because each x in a is in some ui. And they're not in any vn bar, right? Because we have, remember, like all the vn bar and a are disjoint, right? So each x is in a in some ui, is not in any vn bar, right? So it is in some ui prime. Similarly for bn, we're done. So yeah, regular second countable gives normal. Okay, and second we have metrizable space are normal. Metric spaces are normal spaces. So given let xd be a metric space, and given two disjoint closed sets, because, okay, let's do the same thing for a and a. Since b is closed, so we can pick an epsilon a greater than 0 such that it is contained in b complement, right? Because b is closed, and so b complement is open, right? And a is an a and b are disjoint set, right? A is a disjoint set, so a is contained in b complement. So for each a and a, we can pick epsilon such that it is disjoint with b. Okay. Am I going too detailed? But I think it's a good thing to go more detailed, right? And b is in b. We do it by symmetry, right? Pick epsilon b such that this and a are empty. Okay. So remember the collection. We run through all the elements j and all the elements b in b. Now we take u and v, the union of them, but this one, the radius, we all divide by 2. And as you might guess, we do this because we're going to use the triangle inequality, right? So obviously a and b are contained in u and v. So we want to show that u and v are disjoint. To show that, suppose by contradiction, we have an element in here. So z is in some a epsilon a over 2, b epsilon b over 2 for some a and a, b and b, right? Then, by triangle inequality, the distance between a and b, right, can be strictly bounded by epsilon a plus epsilon b over 2. And without loss of generality, one of them must be greater than each other, right? So greater than or equal to, right? Greater than or equal to one of each other. So without loss of generality, suppose epsilon a is smaller or equal to epsilon b, then this is less than or equal to epsilon b plus epsilon b over 2, right? So it's less than epsilon b. So what we get here is that a is in the neighborhood, epsilon b neighborhood of this ball in b. But remember, we require that all such ball in a are disjoint, but now we have an element a and a such that it is in this. So it's a contradiction, so u and v must be disjoint. Okay? So, yeah. So we're done, right? With metric space, right? We have a and u, b and v, and u and v are disjoint. U is obviously, v obviously, they're both open sets, obviously. Right? And lastly, we have compact Hausdorff space is a normal space. Compact and Hausdorff. So recall this lemma from lecture 10. Okay, we have this lemma from lecture 10. So for any compact subspace of a Hausdorff space, for any x not in y, there exists disjoint open uv such that x not in u and y is contained in v. So what we can do here, is that for any b closed, for any x and b closed and x not in b, then b is closed, x is compact, right? So b is compact subspace of x, right? So x is already T3, already regular by the lemma, right? X and x, x not and b, right? At this point, x is already T3. So we push forward to T4. Again, we've been doing this, right? For any a, b disjoint closed, we can just run through the points in a, right? For any a and b, use T3, right? Blah, blah. We've been doing this again. And this gives UA and VA open cover of A and B. Okay, so each VA contains B, and each A is in its corresponding UA, and UA and VA, each pair is disjoint. Yeah, I mean, yeah, I'm just going blindly. So, but remember, A, B are closed. X is compact, so A and B are compact, right? Closed subspace is a compact space is compact. So A is compact. This is a. So, I mean, we already need here is A. A is a. B is also A, but we already need the fact that A is a compact subspace of X. We only need to use that to show that A can be contained in a finite union of UA1 to UAMs. And for B, since all the VA contains B, so does their finite intersection, right? So B is contained in, like, obviously, right, just to match with the A1 and the AMs. And here's my side note, observe that there's disjoint, right? I mean, maybe let's just verify this. So this intersect with those. Okay, suppose you're in UA1, UAM intersect with VA1, intersect VAM, right? Then suppose X is in this, then X is in some, you're in here, right? X is in some UAK, and X is in all VAK, right? Which specifically are corresponding VAK, all VAI to be more precise, right? All VAI, so when I is equal to K, right, to be matching, we see that X is in UAK and also in VAK, which is a contradiction, right? Because we have this. Yeah, so this is really just like observe that they're disjoint. So yeah, this is everything. Normal space, we see that familiar spaces are normal spaces, right? Okay, so let's just summarize this. Compact Hausdorff is normal. Metrizable is normal. Regular and second countable is normal. Okay, so this is everything, and I hope you guys enjoyed this. I'll see you guys next time.